Well then, hello. If you've clicked this video, I hope you're interested in mathematics and hopefully you're interested in polynomials, the greatest type of function in mathematics. Maybe, possibly, I don't know. This is what a random polynomial curve could look like. Of course, it's terrible and really it's way too bumpy to actually be like a simple polynomial, but imagine it was a bit smoother. If this was the case, then you could write f of x, if this was the curve f of x, as x minus a times x minus b times x minus c times x minus d times g of x, where g is another function. It could be anything, but basically g of x or g of t would be defined at t equals a, b, c, and d. What I mean by that is that g and t wouldn't be g of x wouldn't be something like 1 over x minus a, because then the x minus a here would cancel, and if that was the case, then at t equals a, g of t would not be defined. It would tend towards infinity because it would be 1 over 0. And so by saying it is defined there, it's going to be some constant multiplied by 0, and the function f of x is going to be 0. So it's just to be formal, but it's not that important. Um, Basically, you can forget about like all of this if you want, but I'm just gonna keep it there. Um, so basically, you might have heard something along the lines of, yeah, if you have 3 points, you can find a second degree polynomial that will fit those 3 points. And it kind of makes sense, right? Let me draw a uh, second degree polynomial that could fit 3 points at random. So we're going to pick a point like there. Oh, wow, that is small. Uh, we're going to pick a point there, there, and there. Your curve would probably look like. Can I actually make a curve with this? Maybe. Um, it would be something like that, and that would be your second degree polynomial. Of course, this does not draw second degree polynomials, but then it would look like that. And of course, if you have 2 points, it's intuitive that you can have a line, right? Like this would be the x-axis, y-axis, and you could have a line like this that can match any of your 2 points, and you can move one of the points over there, and you can have a line like that, or you can have a line like that. Between any 2 points, you can match a line through them. This is intuitive, like really intuitive. For the 3 points, it's not that intuitive that you can with the parabola. Of course, we're saying that the points are, not something like this right above each other, because then uh, your function, would have to be vertical. Wow, that is huge. And that's not like defined, because usually functions are defined as one like y value per x value, but let's not try to break the system here. And then you might have also heard that if you have like 3 points, like something like this, 4 points, you could match a third degree polynomial through them, and then it would look something like it would go from the negative through there, back here, and then back up to the positives. And third degree polynomials are actually opposite, um, because of course, like a parabola is going to be either like that or like that, because you square the numbers. So whether it's positive or negative, um, your x squared is going to be positive, and if you put like 4x squared, it's going to be positive, and if you put like minus 3x squared, it's going to be negative. But with third degree polynomials, it's going to be x cubed. So when you're in the negative, x cubed is negative, and when you're in the positive, it's positive. So if you put, this would be something like 3x cubed, it's actually negative in the negatives and positives in the positives. And if I put my points differently, then maybe the thing would look like this, and it would be like minus 3x cubed, and in the negatives it would be positive. And so now you might have also heard, if you have n points, you can find a polynomial of degree n minus 1 that will go through those points. Um, so what is the relationship between this and curve fitting those points? Because here the points I chose are all at y equals 0. So this is a terrible example, right? Anyone could do that because you could just say, well, f of x equals 0, and then it's going to be equal to 0 at a, b, c, and d. But 0 is just not a good example. So instead, we're going to be looking for basically the first example I wanted to do. I was listening to some presentation at university at our preparation day, and in the bottom left of their PowerPoint, they had this. And then I thought, hey, can I find a second degree polynomial that will be equal to 4 at minus 1, at equal to 1 at 0, and 2018 at 1. So basically f of minus 1 equals 4, f of 0 equals 1, and then f of 1 equals 2018. And then I thought, hey, I could make a polynomial that's equal to 0 at 0 and 1 and equal to 4 at minus 1, and that would be a good start. So now we have to find a polynomial that's equal to 0 at 0 and 1. So that's easy. That's x times x minus 1. If you plug in 0, the x is 0, and if you plug in 1, the x minus 1 is 0. And then we have to say, let's say that's, how are we going to call that? Let's call that a of x equals that. And then we're going to put a space here. Oh, can you see this? Oh, I'm so sorry. This is so small. Oh my god, that is terrible. Okay, there we go. That is slightly better. I'm gonna need some space too, so this is gonna be perfect. Um, so now we have to look at a of minus 1 equals, now you might already have seen where I'm going to with this, but I'm just going to do it fully, right? A of minus 1 equals 2, and then you could say a of x equals um, 4 over 2 times a of x equals 2x x minus 1, and so a of minus 1 equals 4. And of course this is just 2, but I wanted to do 4 over 2. And now you might have realized that with this principle, I've created a second degree polynomial that's equal to 0 here, 0 here, and 4 here. And I could just repeat and find one that's equal to 0 here, 0 here, and 1 here. Then I could find one that's equal to 0 there, 0 there, and 2018 here. And then you add all of them up, and you get the polynomial that goes through there. And you end up with something like 2x times x minus 1 minus something like 2x minus 1 times x plus 1, and then plus like 1009 x plus 1 times x, something like that. But that's not really interesting. Now you have to try to say, well, can you do this with any polynomial? Like, can you do this with any amount of points? And of course the answer is yes. And the reason you need a degree n minus 1 polynomial to do it is that you have to set all of the other points you're given to 0. So to do that, you have to multiply. Let's say you're given f of a equals 1, f of b equals 2, f of c equals 3, and then on and on and on, and then f of z equals z. No, that would be terrible. Actually, z would be... I don't want to just put 26, but because it's not really mathematical to go with that order. But let's just say some random value, okay? So you have a random amount of points here. It doesn't have to be 26, it doesn't have to be 4. What you're going to have to do is you're going to have to set a first function. Now you can't use a because I've already put it here, so you can go with something like what notation could I use? I'm just gonna pick g, right? G of a or g of x equals x minus a, x minus b, x minus c, x minus z. And now you divide by some like x minus a, and that's equal, and that means that g of t equals 0 for t equals b, c, d, all the way up to z. And g of a equals whatever g of a is, and so it's going to be f of a times a constant, and you don't know that constant, but then you can multiply g of x by that constant, and then you can divide g of x by that constant, and then you'll find f of a. And yeah, that's basically all I had to say. I just think it's really cool that you could write the polynomial of degree n minus 1 as a sum of n terms like this. So you would first go with the a here, and then you would have, this would be like your first one, and your second one might be like h of x, and then you would have x minus b. And so, you would have, here you would have the same line, h of t equals 0 for t equals a, c, d, all the way up to z, and then you would have h of b just isn't equal to 0, and then you can just multiply that specific function by a certain value to get the value you want, which here would be 2, and it's going to be some constant that you can find just by finding actually f of x, replacing all the x's with 2, and then finding what value it gets, and then you divide, multiply, however you want to see it, and then that's your coefficient for that polynomial. And so you're summing up a bunch of polynomials which are of degree whatever this is, and this degree is actually like the amount of terms here between a and z minus 1. And so there's z points here, let's say, and you're removing 1. So for z points, you need z minus 1 degree polynomial. The reason it's z minus 1 degree is that the highest, how is it? I don't remember the term for the highest power in a polynomial, but there is a word for that. I don't even know it in English probably, but it's whatever. So basically, the highest degree term you'll have in here isn't if you go like, well, I'm going to do x times minus b times x times minus z. The way you're going to get the highest degree is simply by multiplying all of those x's together, and once you divide by this x, it's going to go down by 1. So it's going to be z minus 1, the total amount. So yeah, I thought that was quite cool.